Hi, this is Alex from devstories.eu. LiteLLM, the Universal LLM Gateway, episode 10 of 24. There's nothing worse for user experience than a chatbot that displays a loading spinner for 45 seconds simply because an upstream API silently hung. You need a reliable way to sever dead connections instantly so your system can recover. We solve this by taming hanging requests with timeouts. When you route traffic to external language models, network delays and provider outages are inevitable. If a provider stops responding, the default behavior of many HTTP clients is to keep the connection open for a long time. LiteLLM intercepts this problem using two distinct timeout mechanisms. The first is the standard timeout parameter. This setting dictates the maximum total time LiteLLM will wait for an entire request to complete, from the moment it is sent to the final generated character. If you set a standard timeout of 30 seconds and the model takes 31 seconds to write a long response, LiteLLM will abort the request. This works fine for background tasks or short non-streaming generations. However, applying a total timeout to a streaming application creates a structural problem. A thorough response might legitimately take 60 seconds to stream back to the user. If you set a short total timeout to catch stalled requests, you will accidentally kill perfectly healthy, long-running generations. This is where it gets interesting. LiteLLM provides a second parameter called stream timeout. This setting specifically measures the time to the first token. It controls exactly how long the gateway will wait to receive the initial chunk of data from the provider. Once that first piece of data arrives, the stream timeout clock stops, and the connection remains open for the rest of the generation. Consider a concrete scenario. You are routing traffic to a primary Azure OpenAI endpoint. Inside your configuration file, you define your model block and add the stream timeout parameter, setting it to 2 seconds. A user submits a complex prompt. LiteLLM forwards this request to Azure. Normally, the upstream server processes the prompt and returns the first chunk in a fraction of a second. But in this instance, the specific Azure node hangs. The gateway starts counting. 1 second passes. 2 seconds pass. The first chunk does not arrive. Because you defined a 2-second stream timeout, LiteLLM refuses to wait for the standard HTTP timeout to trigger. It forcibly aborts the connection right at the 2-second mark. Aborting the dead request is only half the architectural benefit. By forcing a quick failure, LiteLLM immediately activates your fallback logic. The moment the Azure request times out, the gateway reroutes the exact same user prompt to the next available healthy node in your deployment list. The user experiences a barely noticeable 2-second delay before the text starts streaming, entirely avoiding a frozen interface. You have the flexibility to enforce these rules at different levels. You can apply a global timeout across all routed requests, or you can fine-tune them per model. A heavy logical reasoning model might require a lenient stream timeout of 5 or 10 seconds, while a fast classification model should fail over after just 1 second. The responsiveness of your application is governed not just by how fast your primary provider succeeds, but by how aggressively you force a stalled connection to fail. Thanks for listening. Happy coding, everyone.